good morning, everybody. So I'm going to talk about, generative design, additive manufacturing as a whole. So I only have 10 minutes, so I'll try not to waste too much time. So I'm Mathieu Pérennou, work for Hexagon, in charge of the additive manufacturing solutions within Hexagon, the strategy, additive manufacturing strategy and business development. So yeah, we're talking about additive manufacturing and generative design. So if you look at, everybody says for a long time, if you look at these are like old documents from Deloitte or other sources. There are a lot of advantages in additive manufacturing. It's a disruptive technology, everybody says that. What we're concentrating on today is the freedom of design that additive manufacturing gives you. You saw a lot of cool designs. You see one on top, a wheel hub carrier. This is all great. We see that with additive, we can create very, very fancy shapes. And this is what design for AM is. We talk about design meant for additive manufacturing. If you look at the complete workflow from choosing a material, developing a product that is meant to be made with additive all the way to the quality inspection, you go through all these steps. And talking about design for additive is actually talking about the first part of the workflow. But what you've seen so far is a lot of cool designs. But in design for additive, it means we are designing for a process, meaning that even though you have a lot of design freedom that you can achieve with additive manufacturing, you cannot do everything. So is this working? Yeah. So when you design for additive, it means that you have to consider whether you can actually make the product, and you need to take that into consideration doing your design. And the algorithms we're talking about, like this product, Apex GD, that is developed by Hexagon, is what it's doing. It's coming up with very fancy shapes, designs, but it also checks the manufacturability. So basically, it comes up with like additive manufacturing friendly shapes, things that could be made. So that means that you have to take the additive manufacturing process constraints into consideration in your design. And if you think about it, when you make a part with additive, typically you don't make an end product. It's a near shape, but you have to machine it. And you have to make sure you can machine it, actually. Those very lightweight designs sometimes are very flexible, can vibrate, and just cannot be, if you don't think about it up front, you just cannot machine them. So when we talk about design for AM, we need to have an algorithm that can create fancy shapes. You need to make sure you can actually print it. And you also need to make sure you can actually post-treat machine it, for instance. So you need to have kind of a holistic approach to additive manufacturing when you design. And the machining is actually something that if you don't think about it up front, then chances are you cannot actually make your product. So this is the first thing you need to think of. When we talk about design for additive, you need to think, OK, I'm going to make that part. I need to make sure I can make it. And if you think of a company like Boeing outsourcing some of the production, it means that you have to make sure that when you design, your design department can actually talk and interact with the method planning and the production. I'll come up with a design, and then you're going to try to develop a process that can make it, and then you're going to have some back and forth. If you made that change in the design, if you accept this design concession, maybe the product is easier to make, cheaper to make, etc. So taking like a holistic approach to additive manufacturing means actually breaking the silos between those different departments so that everybody works together, to design the part that you can actually make. And this is what we call, internally we call that co-engineering, where the product design and the process development work together. So along the workflow, you have a little workflow on top. At every step, design for AM and additive manufacturing can help you think differently. For instance, when you design something, you can say, OK, because we are optimizing the parts, according to the performance, it means that you can take the material into account. And you saw it in some of the designs. You can, with the same algorithm, investigate different materials. Here you see a part that I think we have one example on our little booth of a gripper for a packaging machine, made one in PA12, the other one in aluminum, and see what kind of gains you can make in terms of weight, stiffness, but also overall cost. So additive manufacturing and design for AM can help you investigate different materials, make the right material choice. Then this is one of the examples you just saw before. So you see like the optimization being run. Once you've done that, you come with a cool shape. That's not enough. Typically, what you're going to do is you're going to do some part performance analysis. So you check that the part can be made. And you're going to check the manufacturability. This is what we haven't really seen so far, but developing a product doesn't mean you can make it. And like Melissa was mentioning, you can use like simulation software that models and simulates the manufacturing process, so you can check that actually you can make that part, okay? So that you can come up with the product that you know you can produce. Another example, like taking post-treatment machining into consideration, pretty simple. Okay, you see this is like a suspension part. What you see on the right, like the big block, is like what we call the design space. So basically, you see the mechanism on the left. You have in gray, you have the space where you could have material, and then the algorithm will actually take material off that design space to come up with the minimum material that you need. And what you see here is, for instance, in that design space, because you know that you're going to have to machine that part, you're going to have to drill those holes. You need to remove some of that design space to make sure you can make the part. So that's very basic, what I'm showing you, but that's what we mean by design for AM. So taking the additive manufacturing process, but also the post-treatment process into account when you design your product. And that was also said, when you do use those algorithms, it doesn't come up with one perfect solution. It comes with a number of design candidates. And depending on your objectives, you can choose the one that will fit your needs best. It could be weight. I mean, if it's for satellite, maybe weight is really the most important stuff. Maybe that's like a compromise between weight and costs, the amount of machining afterwards, et cetera, et cetera. So that's an example of the project that we just mentioned, was mentioned by Sigurd. And this is also one thing that we haven't said. Additive manufacturing can make very fancy shapes, but if you really want to fully leverage the process, you need to actually, sorry, I didn't want to do that. You need to not only optimize one part, but complete mechanisms. You see an example of that. It's a hinge of the hood of a car. We went from, I can't remember the numbers, but we went from 19 parts to 6 parts. So you see all the benefits that Melissa and others were mentioning. You reduce the weight, but you also you make more complex parts that can integrate functions. So you reduce the number of parts, so you actually improve the issues with like supply chain issues and inventory, etc. These are all the benefits you get out of it. This is another example, and I like that example. It's kind of the same. It's a mechanism for like a bottling line. And you see the mechanism was made of 9 parts, reduced to 1 part. In fact, the shape of the part that is made with additive manufacturing is not like a super fancy shape. It's not like the nice, I would say, marketing part that can show a lot of complexity. But it reduces from 9 to 1. And also you see this kind of like soft shapes are really good because the early design is flat. So you have gathering of waste. And if you're bottling like liquids like Coca-Cola, you have problems of corrosion. With that design, it was actually meant in a way so that the liquid doesn't stay on the part, so then you have a better life expectancy of the part. So again, you see what they went through: design, reduce the number of parts. Like there was a question of weight because there are inertia issues here, and also stress analysis after that to make sure that the design actually can sustain the load and the fatigue purposes. Yeah. So if you try to look a little bit at the future. Today, we've seen a lot of optimization based on mechanical loads, so structural optimization. The future is to move to just mechanical to multi-purpose optimization. So you optimize the loads, but maybe there are like some fluid dynamics or thermal considerations to take into account. So multi-physics and multi-objective optimization. Another point is that you don't just optimize the part. You look at it from with a holistic point of view. You also optimize the process. Take an example of if you use a material that is with like fiber-reinforced material, like a polymer. The orientation of the fibers will change the part performance, meaning that you have to optimize not only the design of the part, but also the process so that you deposit the filament in the right direction so you obtain the right performance. And actually, when you do your optimization, you want to do all of that together. So today, we kind of do that, like I showed you in the previous example, like sequentially. First you design, then you check performance, then you check manufacturability. The objective is to do that all together, so that in one loop, and with the help of machine learning, you can actually integrate all those constraints into consideration at once, and you'd come up with a design that meets all the criteria, including manufacturability. And by doing that and connecting the solutions together, you're also able to develop multiple designs, do like design of experiments to really and like investigate the complete field and help you choose the right design. So the little workflow I show you is the kind of workflow we execute today with the solutions that we have at Hexagon. And the idea is to connect all of that and to integrate all those needs together. The second one, the hurdles of today, because we are an additive manufacturing crowd here. We're all convinced that additive manufacturing is good. But if you talk to many companies, they actually know additive is important, but they don't know how to use it. The hurdles are the quality of the parts still. That's why there is maybe low acceptance of additive manufacturing in the industry yet, so we're working on that, and integrate that in your design as well. And then to help, like I said, I will repeat myself, you need to look at the complete workflow, but also you need to look at what happens before you start making a part. The tools we propose at Hexagon help you better design a part, but the first step is actually be able to identify projects, parts that are fit for AM, from like I would say like a technology standpoint, but also from a financial standpoint. And this is where sustainability gets into consideration. You have to look at the thing from a holistic standpoint. Yes, maybe my part is more expensive to make, so from a manufacturing standpoint, this is not viable, but I save weight, meaning for an airplane, we had a case of like brackets. Replacing all the brackets with an additive manufacturing process was more expensive, but we could save 200 kilos on an airplane. Meaning what? Less fuel consumption, or maybe flying an additional passenger. So the economy, the equation for the economy of the whole thing is not just about the process, but really look at it from a holistic standpoint to integrate everything to calculate the value of additive manufacturing. So with this, I conclude my presentation. Thank you for your attention. We have a little booth. I'm available to answer any of your questions. Thank you.